Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to another edition of the VOC Matric Revision session. Of course, today mathematics is once again in the spotlight. I know that a lot of matrics are looking forward to this session. Maths sessions are very, very valuable, so please take
It's
advantage of.
chemistry.
And also, if you are Oh, sorry, chemistry. I apologize for that. It's actually chemistry today. And if you are perhaps not a matriculant yourself, but you know of someone who could benefit from these lessons, please make sure to share them widely on your platforms. And joining me today, once again, Muntasir, assalamu alaikum.
Wa alaikum salam wa
Muntasir?
rahmatullahi wa barakatuh.
Khair. Okay, so I think without further delay, I said mathematics, but it's actually chemistry. So I'll allow you to continue. And of course, we look forward to another important session. So once again, we're saying please share this wide. And of course, Muntasir will make those resources available for you after the session, inshallah. I mean, without further delay, fight to father.
Okay, shukran. So, as mentioned today, we'll be doing chemistry. This is specifically looking at paper 2, and we'll be looking at a section that students often struggle with, and that is rates of reaction. So, yeah, let us jump straight into it. So, in example 1, we have two experiments that will be conducted. Right? Experiments 1 and 2 are conducted to investigate one of the factors that affects the rate of the reaction of aluminium carbonate with excess hydrochloric acid, HCl. The balanced equation for this reaction is we have 1 mole of aluminium carbonate solid that's reacting with 6 moles of hydrogen chloride, right? And the reaction is favored to the forward, which is giving us 2 moles of aluminium chloride over here, plus 3 moles of water and 3 moles of carbon dioxide gas. They give us the apparatus that is being used, right? As we can see, here's our funnel going all the way down with the hydrochloric acid in it, right? We just fill it up there and it pours in, and this will be drip by drip. So this here that we have over here, this is a burette. Okay, so we are measuring out very small quantities during this reaction because it is a neutralization reaction. And the reason we measure it out drip by drip is because we want to get the exact moment at which neutralization occurs. Okay? Over here, we have the aluminium carbonate. And then over here, we have a type of syringe that's plugged in through this cork. It's going into this Erlenmeyer flask over here. And what essentially is happening in this reaction is as the hydrochloric is being added, the aluminium carbonate is turned into aluminium chloride, which is aqueous, right? So it's going to be the liquid section with some water, and then carbon dioxide gas is going to be released. So what you should be seeing in this reaction is some bubbling occurring beneath the bottom of the Erlenmeyer flask. That gas is going to float up, go through this tube, into the syringe. And what's going to happen? The gas is actually going to do work, or the particles going to do work. And they're going to create a pressure as they enter here, and it's going to push the plunger up as it fills up with gas. And that's essentially going to tell us how much carbon dioxide gas we have collected in terms of volume. Now, as we get down, the reaction condition used for each experiment are as follows. So if you looked at the first experiment here, it shows that we're using 100 centimeter cubed of 1.5 mole per decimeter cubed of hydrochloric acid. Very important, always try to convert these values into decimeters, right? Because that's the standard that we're working. Remember that 1 centimeter cubed is equal to 1 milliliter and 1 decimeter cubed is equal to 1 liter. They state that this reacts with 0.016 mole of aluminium carbonate granules at 25 degrees Celsius. And that's it for the first experiment. In the second experiment, they tell us that we're only using 50 centimeters cubed of 2 mole per decimeter cubed of hydrochloric acid. So here we have a higher concentration, but a lower volume. And this reacts with the same amount of aluminium carbonate at 25 degrees Celsius. 5.1. Okay, so the first question is a definition. Define the term rate of reaction. Okay, so in this case, rate of reaction, we can look at two things. We can look at concentration. We can define it in terms of concentration. We can define it in terms of number of moles. We can also define it in terms of volume. But the important thing is the word rate, and the rate means over time. So we can imagine concentration over time, volume over time, or number of moles over time. Yeah, and for each of those, we are essentially saying that the rate of reaction is the rate at which the concentration of a certain product is produced, or the rate at which the reactants are decreased. Right? And we can look at the formal definitions that they give us here. So here they state change in concentration of products or reactants per unit time, or change in the amount or number of moles or volume or mass of products of reactants per unit time. Okay, so we have those two. And as we go on, we have more as well. Amount or number of moles or volume or mass of products formed or reactants used per unit time. And as we can see, as we mentioned, so those are the things we look at, right? We're looking at moles, volume, or mass, or even concentration, right? As long as you say per unit time, you are in the clear and you guarantee to get those 2 marks. Okay. 5.2. Use the experimental setup above. State the measurements that must be made to determine this rate of reaction. So, using this experimental setup, so we need, first of all, we know it's a rate of reaction, so the first one is time. Time is guaranteed. We need to measure how much time it takes for this neutralization to complete, right? And that also, and the other thing we need to look at is the volume of carbon dioxide gas produced, right? And we can go here and we can take a look, and they state time and volume of carbon dioxide gas produced. Okay. 5.3. Use the collision theory to explain how the average rate of a reaction in experiment 1 differs from the reaction rate in experiment 2. So they wanted to explain the differences. Okay, so we're using our collision theory, and we can just quickly go over that. So if we look here, well, more hydrochloric acid particles per unit volume. So of course, what they are speaking about here is if we look at our reactions, okay, here we have a lower concentration with a higher volume, and here we have a higher concentration with a lower volume. So in order to put this into perspective, we can think of it in this manner. And I'll just do this. All right, grab this over here. Let's add it to current page. Here we go. All right, so let's look at this. So let's imagine the scenarios. So we have a container. All right, there's container 1. This is the volume. We can say this is 100 centimeters cubed. And we have another container, half of that. And this is 50 centimeters cubed. If we visualize things like that, it really does help a lot. Let me just get this, pop this open. Okay, now they're telling us that we have, and I'll do this. Oops, there we go. Here we go, better. So in the 100 centimeters cubed, they tell us we have 1.5 moles per decimeter cubed. So essentially, the particles that we have here, and I don't know why it didn't change. Okay, I did change the color. Let's go back to the pen. There we go. Okay, it's weird. So they're telling us that in this one, let's say we have 1, 2, 3, 4, 5, 6 particles, right? This represents the concentration, right? 1.5 mole per decimeter cube is represented by this. But here we have 2 mole per decimeters cubed. So we can say, let's say instead of this being 6 particles, this is now 9 particles. Do you see that the chances of collisions occurring in the smaller volume are much greater than the chances of collisions occurring in the greater volume? Right? And this means they're going to take a longer time to travel to each other and to orientate themselves and to crash into each other at the correct orientation so that the reactions can take place. Whereas for this one, it's much easier because they're so much closer together. We can have more collisions happening, like more frequently. Whereas the collisions are happening less frequently. So there's going to be less collisions happening over time. So we can have less, carbon dioxide is essentially going to be produced a lot slower in this container with this concentration than in this container with this concentration. Okay, so you can see we can visualize such a thing. And the two things we could visualize, we were speaking about the orientation of the particles, and the rate at which the collisions were occurring. The other thing to take into consideration is the surface area of the particles. Of course, we know that we're both using granules, but if the surface area is different, if we're using a powder, there'd be more particles floating around, right? And then there'll be even more collisions available. So let's go back here. And let me just clear this off. That's interesting. Okay, let's just clear this off. Oh, hold on. I think I have two open. That's why. I do. Oh, okay. Give me a second. Close this. There we go. Now this should work. Right. There we go. Okay. Now, if you look here, they say use the collision theory to explain how the average reaction rate in experiment 1 differs from the average reaction rate in experiment 2. So we visualize it using those two containers. Now let's look at what they say. More particles per unit volume, more particles with correct orientation. We spoke about that. More effective collisions per unit time, or higher frequency of effective collisions. We spoke about that as well. We spoke about the higher rate of reaction as well. So we got all 3 points just by drawing and visualizing the scenario. That's conceptualizing is very important. It's a very powerful tool to use. Your imagination is extremely useful. So, let me go back here. Okay, now 5.4. The average rate of the reaction in experiment 2 during the first 2.5 minutes is 4.4 times 10 to the minus 3 mole per minute. Calculate the number of moles of aluminium carbonate that remains in the flask after 2.5 minutes. So they speak about the average rate of reaction. Okay? And remember, in this problem, we are looking at, and I seem to have split it. Okay, that's unfortunate. Just give me a second. Go back here. Okay. Yeah, okay, it's fine. So they're speaking about the average rate. So remember that in this experiment, we are measuring via the amount of carbon dioxide produced, right? So the equation we're going to want to use, because this is collision theory, we are speaking about particles, okay? And we are measuring the volume of the gas being produced. We are basically going to do this. So we take this here, add it to a new page, and let me get some more information for us. And the other information that we're going to need is the balanced equation. So we'll grab that here as well. Okay, add to new page. Oh, no, not new page, go back. Go back here. 2 seconds, there we go. Okay, excellent. I will add this to our current page. And all I'm doing here is, and it's something you should do, is hunt for all the important information and group them together. It makes it very easy for you to solve these problems. As you can see, there's a whole lot of info that you don't really need. So just put it together, the information that you do need. I did it again instead of just saying to current page. Here we go. Okay. There we go. Okay. All right. That's together there, and we need one more piece of information as well, and we're going to need our concentration. So which experiment are we looking at? Experiment 2. So let's get our information for experiment 2. And we just grab this over here. Okay. Just do a bit of Sherlock Holmes work, some investigation, and we group all our clues together. Right, now we have all our clues. So remember that the rate of reaction is equal to, well, we can say the number of moles over the change in the number of moles, over the change in time taken to produce that number of moles. Okay. What was this question now? Let's just double check. Calculate the number of moles of aluminium carbonate that remains in the flask after 2.5 minutes. Okay, So we want to know what remains in the flask. Let me just put this over here. Okay, so we want to know what remains. So if we look at this equation, that means R, oh, sorry, lowercase r, not capital R, for rate. That means our rate is essentially equal to the final number of moles subtracted from the initial number of moles over a change in time, which is T final minus T initial. Now, what are our clues here? Well, we do have T final. Let's say it's 2.5 minutes. And always look at your units. We see this is in minutes. Are there any other information that's in minutes? Let's just see. Well, our rate. We know our rate is equal to 4.4 times 10 to the minus 3 mole per minute. Lovely stuff. So this means we can actually leave our time in minutes because minutes are going to cancel minutes eventually, right? So we leave it like that. Now we have our time. Our initial time, this is our time final. Our initial time when we started this experiment was at 0 minutes. So we can put that in there. That's our initial time. Okay? And we can double check that on the function as well. Next thing we need to know. We want to calculate the number of moles of AlCO3 that remains in the flask after 2.5 minutes, right? And they tell us 50 centimeters cube of this reacts with 0.016. So we know that initially there's 0.016 moles of aluminium carbonate. So N initial is equal to Al2 N initial for aluminium carbonate is 0.016 mole. Now we can go ahead and substitute this information into our equation. Well, we've got 4,4 times 10 to the minus 3 mole per minute. And yes, I know it's tedious to writing all my units, but it is very, very important. It is the utmost importance that you fill it in. Right? We don't know what the final is. We want to figure that out. We know this is 0.016 mole, and we know that this is over 2.5 minutes. Now we multiply this by this, and we'll end up with NF is equal to, and we're going to say 4,4 times 10 to the minus 3. 4,4 times 10 to the 4 times 10 to the minus 3 is equal to that, times that by 2.5. That gives me a value of 0.011. We add that to the 0.016 because it's going to come over. And I'll just write it over here. We're going to get 0.011 mole. We move this over. And then we're going to get plus 0.016 mole. And our answer for what should be left over in the tube, NF, change, that's correct, yes. And so, 0.0 plus, so 0.028 mole. Right, and let's see if this is the correct answer. Let's double check. Go here. Okay, scroll down. And did I leave something out? Oh, yes, it's the difference. Oh, my apologies. I was supposed to go 0.016 subtracted from 0.011. Yes, I made a slight error with my calculations. So we use the correct equation, right? Delta N over T. We substituted the information incorrectly. But what I forgot to do was to notice that the change in N is the change that we're looking for, right? So delta N is now going to equal 0.011. And then NF is equal to, yes. So I'll just go show you over here. So this is all good. This is wrong over here. But if we substitute it like this, so delta N, we leave it as this. This is the unknown. This is the change in number of moles over 2.5. Right? We'll just substitute this with 4 comma 4 times 10 to the minus 3. Right? And then we got 0 comma 0 1 1 equals the change in n, which makes sense. Change in n is equal to nf minus ni. Right? We want to find out what nf is. So nf is equal to change in n, right? Which is correct. And then we're supposed to subtract the 0 comma 1 1 from the ni, right? And then this is going to be 0 comma 0.16 minus 0 comma 0.11. And this gives us 0 comma 0.5 mole. Right? So if you look here, 0 comma 0.166 was what we started off with. So we're actually going the initial amount subtracted from the final amount, because this is what we started off with, and it's greater than this value over here. So that's going to indicate the change. Right. Let's look at the next one. Let's see here. Next page. Okay. So calculate the maximum volume of carbon dioxide that can be prepared at 25 degrees Celsius in experiment 1. Take molar gas volume at 25 degrees centigrade as 24,000 centimeters cubed per mole. Okay. Now, we'll go here. Where's my whiteboard? Okay. All right, open it up. Okay, so let's take a look here. Let's go to the memo and see how they went about it. So what they did was, if you look here, they state use the mole ratio NCO2 to NaL to CO3. We find that it is 3:1, right? That's the molar ratio. And we can double check that if we look at, and what I actually want to do is I want to grab this and pull this back over here. Nope, okay, it's not working. So we leave it like that, right? And if we scroll up and we look at our balanced equation, look here, right? It's 1:3. So for every 1 part of aluminum carbonate, we're getting 3 parts of carbon dioxide. So we need to consider our mole ratio, because they are asking us to calculate the maximum volume of carbon dioxide that can be prepared from this, right? That can be prepared from 0.016 mole aluminum carbonate. So theoretically, we should be able to get, right, according to the ratio, theoretically, we're supposed to be able to get 3 times this amount in terms of carbon dioxide. Okay. Now we go back to the memo. Not here. Okay. Now we look at this memo and we'll see that they go 3:1. Then what we need to do is, because we're calculating number of moles and we need to use the molar ratio, right? We can say that number of moles is equal to the volume over the volume at molar volume, right? So normal volume divided by molar volume. We know that our molar volume is 24,000 centimeters cubed per mole, but we can convert that to 24 decimeters cubed per mole, which is way more useful for us to work in. Right. So we can go down and we look at what they did. So they said N equals 3 times the number of moles of aluminum carbonate, and we find that the number of moles of carbon dioxide is 0.048 mole. We then make that the subject of the formula, because the question asked, and if we double check, we'll go back and take a look. The question asked us to calculate the maximum volume of carbon dioxide, hence us using this specific equation. Right? We're using the maximum, we want to find the maximum amount of carbon dioxide in terms of volume. So then we say NCO2 is equal to V over Vm. We substitute our values in, the 0.048 mole that we got from the molar ratio, put that in there. The 24 decimeters cubed can go in over here, right? And then we just multiply and we'll find our answer will be 1,152 decimeters cubed. So fairly simple. Okay. Let's look at the next problem. Let's see here. Open this up. There we go. Now, experiment to do. Try on your own. The reaction of calcium carbonate and excess dilute hydrochloric acid, HCl, is used to investigate one of the factors that affects reaction rate. The balanced equation for the reaction is calcium carbonate plus hydrochloric acid reacts to give calcium chloride plus water plus carbon dioxide. The same mass of calcium carbonate is used in all the experiments, and the temperature of the hydrochloric acid in all the experiments is 40 degrees Celsius. The reaction conditions for each experiment are summarized in the table below. In experiment A, we have the same volumes and the same concentrations for all three experiments. The only things that are differing is the state in which they are divided. We have granules, lumps, and powder. As we know, the bigger the pieces you are using, the longer it's going to take for the reaction to occur. All right, so the reaction rate is going to be lower because there's less surface area. So for this investigation, write down the dependent variable and the independent variable. Okay, and if we go to the memo over here, they simply tell us that this is the reaction rate, which is your your dependent variable, and your independent variable is going to be your surface area or state of division or particle size, right? So your reaction rate is dependent on the state of division. That's what they are basically telling us. 5.2.1. Okay. The carbon dioxide gas, CO2, produced during experiment A, which is granules, is collected in a gas syringe. The volume of gas collected is measured every 20 seconds, and the results obtained are shown in the graph below. So for experiment A, we can see here's the information for our graph. We can see that there is a dramatic increase in terms of the amount of carbon dioxide produced, right? We can see this is a steep incline at 20 seconds. At 40 seconds, we can starting to tip off. The rate of reaction is starting to decrease. Here it's decreasing even further. And then until it gets to 1 minute, we notice just shortly after 1 minute, the volume of carbon dioxide just levels out. Right? No more carbon dioxide is being produced. This means there is no rate of reaction as no carbon dioxide is being produced due to the volume staying constant for another minute. So, what can be deduced from the graph regarding the rate of reaction during the time interval? Well, we can say that from 20 to 40 seconds, right, the rate of reaction is slowly decreasing. And we can say from 60 to 120, the rate of reaction has decreased and come to a complete halt where there is no more carbon dioxide being produced. So, 5.3. Calculate the average rate in centimeters cubed per second. So notice they want it in volume over time, at which carbon dioxide is produced in the experiment. Okay, so they want us to calculate the average rate. Well, we can see that there is a rate of reaction from 0 to 60 seconds. So if we had to solve this problem, let's just do it over here on the side. Right? If we had to solve this problem, we could simply say that the rate of reaction is supposed to be change in volume over change in time. Right? This is much like finding a gradient. If we look at this graph over here, we're going to do change in y over change in x. Right? And we're going to select this point and we're going to select this point. Okay? This point here is basically, if we look at it, it's 60, 500. And this point here is 0, 0. So our rate of reaction is going to be, wow, volume is 500 minus 0 over 60 minus 0. Right? This is centimeters cubed. This is in seconds. So we essentially have 500 seconds. 500 centimeters cubed over 60 seconds. And this should give us, let's see, an answer of 30, I believe. Double check. No, 8.33. Math is off. 8.33 centimeters cubed per second. And that should be our answer, and that should be how we solve it. And we can just double check the memo. Over here, and there we go, 8.33 centimeters cubed per second, right? So we are on par now. And that's for 3 marks. So very, very easy indeed. Now let's go over here. So how will the volume of carbon dioxide produced in experiment B compare to that produced in experiment A? Choose from greater than, smaller than, or equal to. Okay, so let's see. The volume of A compared to B. Well, let's see. This is granules, this is lumps. Well, B, because it's lumps, will have less carbon dioxide produced than the granules. So we can say that for B, that it will be smaller than. Okay. 5.5. A graph is now drawn for experiment C on the same set of axes. How will the gradient of this graph compare to the gradient of the graph for experiment A? Choose from greater than, smaller than, or equal to. Well, now we are comparing C to A. So if we scroll up, well, C is a powder, so the particle sizes are a lot smaller than that of granules, and that means that the gradient for our rate of reaction is going to be much greater. And we can imagine that. I mean, if we go over here, I'll call this this is experiment A, right? This would essentially be experiment C. We can imagine that it's this, and then it peaks of somewhere over here, and then it flattens out. This we'd call experiment C, and experiment B would be this one over here, right? It goes like this. The gradient's a lot more shallow, and eventually it goes up, and then it peaks off somewhere over here, right? And we can see that if we had to measure the gradient for each function, this is B. If we had to measure the gradient for each line, we see that the gradient is a lot steeper here than it is over here, and then it is over here. Right? And that's how we know. So C will be greater than A. Okay, clear that off. Now, then they state, use the collision theory to fully explain your answer. Well, here we're going to speak about surface area, we're going to speak about orientation, we're going to speak about particle size, we're going to speak about number of collisions, and we're going to speak about frequency of collisions. And then, boom, you'll get your 4 marks for that. 5.6. Assume that the molar gas volume at 40 degrees Celsius is 25,7 decimeters cubed per mole. Calculate the mass of carbon dioxide, calcium carbonate used in experiment A. Okay, so what information do we have about experiment A? We know that it's granules, right? Here's the information for experiment A. This is the final volume of gas produced at 500 centimeters cubed. That's correct. Okay, this is molar gas volume. Calculate the mass. Okay, no problem. So what do we do here? Let me just grab this. So once again, the important word to look at is molar gas volume. That gives you a hint as to what equation it is that you need to use. And the equation we're going to use is essentially N is equal to V over Vm. Right? So we need to calculate the mass of calcium carbonate used in this experiment. Okay. So now we just go, well, let's find the number of moles of carbon dioxide, right? And we know that the volume of carbon dioxide produced was 500 centimeters cubed. We convert that to decimeters, so that's going to be 0.5 decimeters cubed, right? We divide that by our 25,7 dm cube per mole. Remember, this is for carbon dioxide. And we find that the number of moles are going to be 0.5 divided by 25,7 should give us a value of 0.02 mole. Sorry, no, sir, 0.019. I don't round that up. 0.019 mole. Okay, cool. Now, the next step, we have to look at our balanced equation, and we need to look at molar ratios. And we're going to compare the calcium carbonate to carbon dioxide. So we go up. Oh, 1 mole of calcium carbonate to 1 mole of carbon dioxide. So therefore, the calcium carbonate used up would be the same value that we just calculated, 0.09 mole. So we can say, well, we have 1 mole of calcium carbonate to 1 carbon dioxide. Therefore, the number of moles of CaCO3 produced is equal to 0.019 mole. But that is not the end of our problem. They asked us to calculate the mass of carbon dioxide. Well, we need to calculate mass. We have number of moles. Immediately, we should know we need to use the equation N equals M over M. We just rearrange it, and we're going to get M is equal to N times molar mass. Now, this is 0.019 mole. I'm just going to look for the molar mass over here. Right, where's the memo? Open this up. There we go. And if I scroll down, here we go, 0.019, which is what I got. Right, and the molar mass of calcium carbonate, they're not showing it to me here. Okay, so I'll just get them, we'll just calculate it. We'll go to our periodic table. There we go, PubChem. And let's get our values. So, molar mass. Okay. Calcium is group 2, 40,08. All right, so let's just make a note of that. All right, so we got 40,08. Carbon we know is 12, and oxygen we know is 16. So let's just work it out. This is 16 times 3. We're adding this all together. All right, so I've got 416 times 3 plus 12 plus 40,08. And that gives me a value of 100,08 grams per mole. And here we'll find, we multiply that by 0.019, and the mass is 1,9 grams of calcium carbonate used. And are we correct? Let us double check. Back here. And there we go. 1,95. We got 1,9. Okay, there we go. Easy peasy lemon squeezy, not too hard at all. Okay, if you would like the questions, okay, or you need some further assistance, you can go onto the Intune website where these documents are available, the questions with the memos. All right, you just go to www.intune.co.za, and you click on the home tab. You'll see a bar scroll down, and you just select the VOC sessions, and you will be able to access all of these. Okay. Yeah, and that's it for us for today. So if you need any further assistance, like I said, just contact the website, and yeah, we'll be able to assist you further. So enjoy the rest of your day. Assalamu alaikum wa rahmatullahi wa barakatuh. Okay. All right, to interfere.
Then, all the best. Jazakallah khair. Of course, that's been our chemistry session for today. And Jazakallah for your participation. Well, of course, that's it for today's session. Once again, don't forget to check out the sessions on YouTube and Facebook. They remain up there for the duration, and of course, also share them with those who might need them most, particularly matriculants if you're not a matriculant yourself. From myself, Muhammad Fasih Peterson, I bid you assalamu alaikum wa rahmatullahi wa barakatuh.